So that's what a tensor network might look like for Wigner measuring his friend. Now, once this happens, and assuming that we now collapse the three participants into black holes, we can now follow them. And these tensor networks begin to grow. They begin to grow just because wormholes have this growth property. They tend to grow. And in fact, they tend to grow very quickly. That's the increase of their complexity in another language, but I don't want to talk about complexity, so we'll just say they grow, and they do. So after a while, after having done the measurement and collapsed the three participants, you will have some kind of tripartite wormhole, but it will have some obstruction in it. And that obstruction is very interesting. It represents the GHZ character of the measurement, or the state that's produced by a measurement. But on the other hand, it now becomes an object. It's an object down deep in the wormhole of a tripartite wormhole system. We can think of it as a physical structure whose properties, in fact, reflect the duality between Copenhagen and Everett. I'll come back to what I meant by that in a moment. All right, let's. There are wormholes or Einstein-Rosen bridges. Don Marolf and his colleagues have studied them at great length, which are smooth. They are the analog of the thermofield double Einstein-Rosen bridge for two particles, for two black holes. They're smooth, they have smooth geometries, and one would expect that if somebody jumped in over here and somebody jumped in over here, they might meet, and you might even expect that three people could meet in the center. Okay? The GHZ brain, whatever it is different than this. It's fundamentally different in that no two observers can ever detect each other when they fall in. Here's what's known, incidentally, just from an information theory point of view, or it's not known, it's suspected by these authors and these authors here, that if you try to distill different kinds of entanglements out of these smooth wormholes, they have very, very little, if any, GHZ entanglement. They don't contain any of these GHZ entangled triplets. On the other hand, this GHZ brain that we constructed by making a measurement in this way is full of GHZ states, lots of them, and we could distill them. This distinction is invariant under local operations. On operations that take place at the three ends locally, this distinction. So this is a different kind of beast than this. Whatever it is, it's a different kind of thing, but it is a thing. What do we know about it? Well, from the Copenhagen side, we know that no two of them can send messages which will meet in the center. That we've established on the basis of the Copenhagen interpretation. Once the measurement is made, it snips the Einstein-Rosen bridge, and there's no possibility anymore of meeting at the center. That's presumably true well, yes, that should be true. On the other hand, from the Everett point of view, what you create is a three-sided Einstein-Rosen bridge, and each side is entangled with the union of the other two. This presumably means that a message can be sent if Wigner and his friend cooperate in some way. If they can cooperate in some way, then a message can be sent into the interior. This would be the expectation. And if that message was sent in from the other side, they should be able to meet in the center. We do have entanglement between this side and this side. We simply just don't have entanglement between any pair. The suggestion would be that a message can be sent, messages from the two sides can be sent that would meet at the center, but only if Wigner's friend and Wigner can cooperate in some way. More than cooperate, they basically have to reverse the measurement process. How do you do that? So I'll give you one algorithm, protocol for doing that. Einstein is going to help them. Einstein is going to observe Wigner. Remember, Wigner's friend observed the cat. Wigner observed his friend, and now Einstein is going to come and observe Wigner. Now, if Einstein observes Wigner in the same z basis that Wigner did his experiment, all he does is confirm. All he does is confirm and get the same answer that Wigner got. What happens is you get a bigger cat state. You get state 1, 1, 1, 1 plus 0, 0, 0, 0. Okay? It's boring. It's not very interesting. What's very interesting is what happens if Einstein does a little trick. He measures Wigner, but in the x basis. In a conjugate basis, here's what the x basis, 0 and 1 mean the z basis, sigma z. Left and right mean the x basis, sigma x. Here's the relation between the z basis and the x basis with sigma with square root of 2 set equal to 1. Okay, we don't need any square root. Okay, so let's see what happens. We start in the GHZ state, and now Einstein is going to come along and see what happens. We start in the GHZ state, and Einstein is going to make a measurement of the last qubit here. This is now our qubit description. Is going to measure the last qubit, but in the x basis. So what we'd like to do is we would like to express this state in the x basis of the last qubit. That's easy to do. 0 is left plus right. 1 is left minus right. If we combine them together, what we find is left, Einstein having measured left, is correlated to 0, 0 plus 1, 1. This is an entangled state. So by virtue of having measured in the x basis and having detected left, Einstein has pushed this back to the original entangled state between the cat and Wigner's friend. On the other hand, if he measures right, he still projects this back to an entangled state, but it's the entangled state 0, 0 minus 1, 1. So offhand, Einstein may know which of these two is correct, but nobody else, as far as everybody else is concerned, we don't know whether it's this one or this one. We don't know which entangled state it is. Can Einstein do anything to make sure that you get back to the particular initial entangled state that the cat and Wigner's friend began in, namely this one? Yes, Einstein can do something. Here's what he does. If he detects left, he does nothing. Why? Because he's got the right state on the other half of the system. If he detects right, he simply acts with z, with sigma z, on Wigner's friend. That means he flips the sign of this piece here. He flips the sign of the wave function of Wigner's friend and returns the state to 0, 0 plus 1, 1. In other words, by taking the classical information that he has after he does the experiment and using it to decide what operation to do, nothing or operating with z, he inevitably returns the cat and Wigner's friend to the original entangled state. And that's interesting. Somehow, what has Einstein done? He's reversed the measurement that Wigner did. He's reversed the measurement and basically got back the original entangled state. What does that mean in terms of wormholes and so forth? Well, if we have lots and lots and lots of qubits, and we apply exactly the same logic, after Einstein measures Wigner and the cat and Wigner's friend will be in one of many, many states. Einstein will know which one, but it'll be in one of many, many states. For example, Einstein might have measured left when he measured Wigner, in which case the cat and Wigner's friend are projected back to the original entangled state that they started in, which we'll assume had a nice wormhole. On the other hand, he may find Wigner in some other state. Then there will be entanglement between the two sides, but the entanglement will presumably be of some other kind not consistent with a smooth wormhole. That would be the expectation, that you have a mess in here. A mess in here, if you unitarily rotate a state with a nice wormhole, unitarily rotated on one side, you get a mess. That's known. All right, so there's lots of terms here. Most of them involve states which are bad on the inside. They are not nice wormholes, but Einstein has some classical information. And he can take that classical information and use it to perform a unitary operation on Wigner's friend again. Exactly the same kind of logic will bring the cat and Wigner's friend back to the smooth wormhole state, with Wigner being either this, or that, and Einstein knowing it. In fact, Einstein will be entangled with Wigner. So Einstein can use the trick of making the measurement in the x basis to reverse the measurement and to bring the cat and Wigner's friend back to the state where, in fact, somebody can jump in and meet in the center. That's how they would test that this protocol actually worked. What's the result? The result is experiments can be reversed. Oh, there's an important point here. Let's go back a step. One important point. Everything that Einstein did involved Wigner and his friend and not the cat. So this was a case where by manipulating Wigner's friend and the cat, he made it possible, Wigner's friend and Wigner, he made it possible for the cat and Wigner and the other side to communicate something into the interior. So it's consistent with the GHZ property.